Now let's talk about a topic called reversible steady flow work. Remember when we had a closed system and we talked about boundary work and found how useful and important boundary work is and was? Actually, that was reversible boundary work. It's reversible because remember we always assumed that there was no difference in pressure within the cylinder, right? And so the pressure on the face of the piston, the pressure on the head of the cylinder were always exactly the same, regardless of whether we had the piston moving. We assumed there was no friction. All these things were eliminating irreversibilities, and so the boundary work equations we had before were all reversible boundary work equations for closed systems. What about not boundary, but what about work for steady flow systems? So systems that instead of being closed are open and have mass flowing through them, where they're either doing work, where the fluid is doing work on a gas. What about where the fluid is flowing through a system doing work, or shaft work is coming into the device doing work on the fluid? What about those types of systems? Well, we can write an energy balance for an open system that looks like this equation. So we can have a differential amount of heat transfer, say flowing out, and a differential amount of work done by this system. So this is a turbine, for example, with, say, steam flowing through it. And really, it's the change in enthalpy, kinetic energy, and potential energy of the steam that does work and turns the shaft, right? And so we're talking about steam, let's say, moving through a turbine, and this differential equation is talking about just a differential change in the steam as it moves through that turbine. Now, since we can write the differential heat transfer for a reversible system as TDS, and we can write TDS as dH minus VdP, we can make some interesting substitutions here for TDS, for example, and therefore the reversible steady flow work. And so here's what we end up with is dH minus VdP. Now, one thing to note here, why are we talking about reversible systems? I mean, aren't real steam turbines irreversible? Aren't they real? Don't they have some irreversibilities, some friction, and etc.? Well, yes, of course they have. But remember, one of the things we're trying to get at is what's the best we could ever accomplish, and how do we calculate the limits of what could be accomplished, so that if we've got a turbine that's 99.9% efficient, we don't beat our head against the walls trying to get that other 0.1% efficiency out of it. It's a fool's errand, right? There's no point. Where is the limit where we can say, okay, that's good enough because it's just not worth our effort? Let's not waste our lives trying to make a better steam turbine if we're already at one that's extremely good, right? There's no point. So we might want to investigate some other device or something else if we want to increase efficiency further. So anyway, that's why we're talking about reversible devices. It's because we're trying to find the limits of what we can do, and not just understand it intuitively, but calculate it mathematically. So let's make this substitution in the energy balance, and then let's move the terms to the other side, because you'll notice that the differential enthalpy change cancels from both sides of the equation. We can move the negative VdP to the other side. And now we've got an equation that's talking about the work done by a turbine, or essentially the work done by the gas as it flows through the turbine that comes out of the turbine, and terms that include and account for the kinetic energy and potential energy change of the fluid as it flows through the turbine. Now we can integrate this equation through the turbine and calculate the total amount of work done per unit mass as the mass flows through the turbine, doing work on the turbine blades, pushing the turbine blades. Notice we've just moved the negative sign to the other side for our convenience. And we've got, delta KE and delta PE because the change in the kinetic and potential energy of the steam or whatever fluid it is that flows through this turbine is a property, right? It's completely a property of that fluid, and so we can talk about delta, a change from state 1 to state 2, where state 1 is the inlet, state 2 is the exit. But we have to integrate the other term. The VdP term has to be integrated because the particular way that the specific volume depends on pressure and the details of the process that are going on inside of the turbine mean that that integral will take on different values. In other words, this is a path-dependent thing, whereas the kinetic and potential energies are not. Now, as a matter of fact, most of the time the kinetic energy and potential energy of the fluid flowing through the turbine, those changes are so small by comparison to the other terms that it's convenient to just cancel them and neglect them. There's no point in thinking about them most of the time. And we end up with an equation that is for steady flow reversible work rather than reversible boundary work like we had before, and it's that steady flow reversible work is equal to negative integral 1 to 2 of VdP. Notice before, for closed systems, it was that the reversible boundary work is the integral from state 1 to state 2 of PDV. It's kind of interesting that we've just sort of flipped the variables around. One's for open systems and the other one's for closed systems. Now this one's really useful because so many systems are open systems. But what about if we talk about reversible work for an incompressible fluid? So if we think about a pump or something like that, or maybe even air where the air really doesn't compress much, say as it goes through a carburetor. In fact, let's put the kinetic and potential energy terms back into the equation. If the fluid flowing is incompressible, we can pull the specific volume out because its specific volume doesn't depend on pressure. It's just a constant. That's what we mean by an incompressible fluid. In that case, we end up with an equation that says that the reversible work is the negative of V delta P, and of course that's just the change in pressure but between state 2 and state 1, the entrance and exit, and the changes in kinetic and potential energies. And actually, you've already dealt with this equation if you've taken any fluids classes, because you've probably dealt with pumps in your fluids class. And so this is an equation that would allow you to calculate how much work is required to take, say, liquid water from one pressure to another in order to compress that liquid. And you might not recognize it right now, but that first term, V delta P, is an equation you would have used. That would be the primary portion of the fluid power change across the pump. Often the kinetic and potential energy changes are negligible. Now this is not always the case. Some pumps are really good at generating kinetic energy, but not necessarily changes in flow energy, which is the V delta P term, the pressure change term. So a lot of pumps are actually sort of kinetic pumps where they generate a lot of kinetic energy in the fluid, and then you neck it down at the outlet, and the reducing fitting actually trades off. No, I'm sorry, it'd be the other way around. It'd be a diffuser. But that device trades off kinetic energy and flow energy. And so the kinetic energy may go down, but the flow energy, or in other words the pressure, will go up. Now some pumps are positive displacement pumps, like in hydraulic systems. And in that case, the pressure itself is typically what's increased, not so much the kinetic or potential energy. And often the potential energy change is negligible in all of these cases. But this is an equation you've probably dealt with. You may not recognize it yet, though, because in most fluids classes you deal with density, or more usually specific weight, where specific weight is the acceleration of gravity multiplied by density. But think with me for a minute. The specific volume is just the inverse of density. So have you ever seen a delta P over rho type term in any of your fluids classes, or perhaps a delta P over gamma, where gamma is the specific weight, or in other words the acceleration of gravity multiplied by density? We're actually playing with something you've probably seen before. As a matter of fact, if you're just talking about a simple length of pipe with fluid flowing through it, you've probably used this equation before. Have you ever, you probably don't recognize it, but in fact it is actually Bernoulli's equation. And if we rearrange it a little bit, you might recognize it. So again, if you've dealt with a difference in V squared terms and GZ type term, you probably talked about head before, which is the delta Z term, the Z2 minus Z1. If you take this equation and you imagine replacing the specific volume with 1 over the density, and then you divide all three terms by the acceleration of gravity g, you will probably recognize this immediately as Bernoulli's equation, because you can talk about elevation head, that's the delta z term. You can talk about velocity head, that's the v2 squared minus v1 squared over 2g. And you can talk about pressure head, or maybe you called it flow energy, I don't know, or flow head. It depends on what you called it. But the point is that all these terms, these are things that you've used before. So basically Bernoulli's equation, that is sort of the core of many fluids classes, is really just derived from an energy balance, or at least it can be derived from an energy balance. So it's interesting that sort of a whole class is a footnote in thermodynamics. And this is good for all sorts of things. Like I said, straight lengths of pipe. It's good for carburetors and things, where you have venturis. It's good for all sorts of things. A very useful equation, and then it comes from conservation of energy. So this flow energy equation we've come up with is actually really useful. There's other things we can do with it, though. We can think about maximizing or minimizing work, because if you think about this, it's not exactly this way, but you can think of it this way. If the specific volume term is, larger and larger and larger, then it's almost like the right-hand side of the equation gets bigger and bigger. Think about integrating, a pressure change from, 100 kilopascals to 1 megapascal. And let's say that you integrate it with a specific volume that is pretty small, right? So a specific volume that is a really high-density fluid. Let's say you're compressing mercury for some reason, okay? Well, then the specific volume of that mercury would be very, very small. But what this predicts is that if the specific volume is bigger, like the specific volume of water, it's going to take more energy, more work to compress it up to a higher pressure. Similarly, it would take an even larger amount of reversible steady flow work to compress something like a gas, because a gas has a very high specific volume. So the bigger the specific volume, the bigger that integral is going to be on the right-hand side, and the more work is going to be required. And this should help explain why when we considered a steam cycle before, where we've got a turbine and a pump and all these things. Remember, we considered this and we said, well, this seems crazy. Why do you boil off the water, right? It's in liquid form. You boil it off, so there's all this energy you dump into it to change the phase, let it go through a turbine at high pressure, and then run it through a condenser, where the condenser does nothing more than condense it back and change it from vapor into liquid and throw away all that energy. I mean, it seems like you're intentionally harming the environment or something, right? Because you're putting all this energy in just to throw it away. I mean, don't you understand the latent heat of vaporization, right? Well, actually, the reason for this is because we do understand it, right? In fact, we understand reversible steady flow work, and you know that actually, if you try to replace that pump with a compressor and don't condense out the vapor into a liquid, and rather you let a gas flow through it, guess what's going to happen? That compressor will require a heck of a whole lot more work, and a much larger percentage of the work produced by the turbine will have to go back into driving that compressor just to keep the cycle running, because of this equation, this reversible steady flow work equation that says, look, if you have a very high specific volume fluid, like steam flowing through a turbine, you can get a lot of work out of it. But if you have a high specific volume fluid going through a compressor, well, then that compressor is going to require a whole lot of work. Much better to have a very low specific volume fluid, like liquid water, flowing through a pump on the left-hand side, so that it simply doesn't require very much work. So at first blush, you might look at this and say, well, this is not right. There's something afoot here. Maybe, big coal is trying to burn more coal and sell more coal. No, there's nothing about that. This is just basic physical principles about the way things really work. And you have to understand them before you can be effective at increasing efficiency. Trust me, the power plant wants to buy as little coal as possible. If they could operate all year long off of one lump of coal and generate just as much electricity, they'd do it. But hopefully now you understand that there's simply not that much energy available in a lump of coal. There's not enough energy in that lump of coal to drive it if all you do is chemical reactions. On the other hand, if we can figure out a way to do nuclear reactions and take the hydrogen and react it and do nuclear fusion, okay, that's a totally different thing. But if all we're doing is burning chemically the coal, there's only so much chemical energy in it. And so it's helpful to understand this so that we don't have a fool's errand running around trying to make things more efficient when there's just not much available. I mean, do you walk around collecting aluminum cans so that you can turn them in and make a living? Well, if so, you're probably pretty desperate, because that's not necessarily the most efficient way of making money, right? I'm not saying it's a bad thing to do it. I'm just saying that there are better ways, there are more efficient ways of accomplishing your goals of, in this case, making money. So this also is why compressors are cooled, because if you take a gas and you compress it, it turns out its temperature goes up. If the temperature goes up, then its specific volume also goes up, its density goes down. And so if you're trying to compress a gas that has a very high specific volume, it's going to take more work to do it. So compressors always include cooling, because what you want to do is decrease the specific volume of the gas as you're compressing it. Now you might look at this and say, well, wait a second, I thought you said that isentropic processes are the most efficient. That, that's the type of process that you want in order to require the least amount of work and, generate the most amount of work in work producing devices and so forth. Well, it doesn't seem fair, right? You're contradicting yourself. You're saying that there should be some heat transfer. Well, there's no contradiction here, because what we're really saying is that, look, when you compress a gas like air, its temperature is going to go up, and let's just say you don't cool it, right? Let's just say you put it into the can there, the tank, as this really hot fluid. What's going to happen? Well, you're going to lose that energy anyway, right? The amount of energy in the gas is going to go down no matter what you do, because you put hot, gas into this cold tank, and you're going to lose energy. Now, of course, you could say, well, let's insulate the tank, and that's a different type of compressor. But if we just have a simple steel tank and you put hot gas in it, it's going to come to equilibrium with the surroundings, probably by the time you get out your nail gun or your impact wrench or any other thing like that. It's probably going to be cooled down by the time you get around to using it. So we could either choose to throw away the energy while we're compressing it so that it requires less work to compress. And so, yeah, sure, we don't put quite as much energy in the fluid or the air, because some of the energy left as heat. But it won't require as much work. We don't have to put as much work into the fluid in the first place if we cool it during compression rather than cooling it while it's in the tank. So that's a clever way to use this, this fact that flow work, reversible steady flow work, depends on the specific volume of the fluid, and you always want to compress a fluid that has the smallest specific volume possible, and you want to expand or get work out of a fluid that has the largest specific volume possible.